Welcome back to our second video on the least squares approximation. In the previous video, we took a look at 4 data points in the plane, and we came up with a least squares line that best fit those points and related it back to the closest vector properties, matrices, and trying to minimize the square distance between the actual line itself and each of the data points. In a lot of areas, this approach is used. For example, in Hooke's law, when we apply force to a string, the length of the spring will be a linear function of force. When people do lab experiments, the data isn't always clean and perfect, so you might have a table of forces in ounces and their corresponding lengths in inches, and you want to come up with a model that best describes that relationship. So that would be one example. Another could be insurance companies. They might want to look at, based on their customer's age, what's the probability that they fall ill or worse, and then they can come up with their insurance premiums that way. So they also use least squares to come up with models that will help them come up with insurance policy premiums. One last example I'd like to look at is extending this idea out to parabolas. So suppose that you have a data set that might not be best modeled through a linear function. So for this one in particular, I have the points 1, 7, 2, 2, 3, 1, and 4, 3 plotted in the plane. And I think we can agree that we can sort of see a parabola going through these or attempting to go through these better than a line would. So we can extend the idea of least squares approximation up to a parabola if we find that a quadratic model is more appropriate than a line would be. So consider, again, these 4 data points. Just like before, we're going to go and we're going to solve for A, B, and C, and you can call them A sub 0, A sub 1, A sub 2. It really doesn't matter what you call them, but we're looking for the constant term, the coefficient of x, and the coefficient of x squared. And again, like before, you want to start by just thinking of this as I'm trying to solve another overdetermined system. I'm looking for I'm looking for the value of 3 different unknowns with 4 equations because I have 4 inputs and 4 different outputs. So just like before, I plugged in 1 for x, and I got out a plus b plus c equals 7. You can plug in 2 for x. That'll give you out a plus 2b plus 4c. Notice that we square the x here, unlike in the linear example from before, and that output is 2. So I color-coded them as I did before. Now, our matrix C, as we spoke about in the previous video, matrix C holds the coefficients of the x term. In this example, it'll also hold the coefficient of the x squared term as an additional column. And it also holds a column of 1s, just like the last example. That's for the constant term. So let my matrix C consist of 4 1s. That would be for the 4, constant A terms that I have. Then my next column will hold the coefficients of B. So I have 1b, 2b, 3b, and 4b. So I'll just put those in their own column. And then the last column will hold the coefficients of C, 1, 4, 9, and 16. So that's the new addition to this problem that we didn't have before, this extra column of coefficients of C. Your Y vector, just like before in the linear example, this will be the output all in one column vector. So 7, 2, 1, and 3. And again, it's important we preserve the order. If I'm going to go red, green, blue, purple, I have to make sure I follow that order down every column. So next, I'm going to transpose matrix C by writing it out as my rows turn into columns. That's a 9, 1, 4, 16. And I multiply that by my original matrix C. And just like before, mentally, we want to think about dimensions. This was a 3 by 4 matrix. This is a 4 by 3. So the result is a square 3 by 3 matrix. And when we multiply these out, we get 4, 10, 30, 10, 30, 100, and then 30, 100, and 354. So you could either do the math out yourself, or use a calculator to come up with these. Next, we do C transpose times Y. So I'll take my C transpose matrix from the previous step, and I'll multiply that by vector Y. I have a 3 by 4 and then a 4 by 1, so I end up with a nice 3 by 1 matrix. I'll get out 13, 26, and 72. For the next part, the worst part, I next have to multiply, I next have to invert my matrix from step 2, my C transpose C matrix. Because these numbers are terrible, you have my permission to use a calculator to get the inverse rather than tedious amounts of row operations with this and the identity matrix augmented on. So assuming that is done, you will get out all sorts of wonderful decimals in the matrix. From a practical standpoint too, it's just easier to use the calculator for this. Negative 1.25 and 0.25 at the end. And then just like in the linear example, so again, the process is the same. We just have an extra column on C, so then that turns into some bigger matrices along the way. For step 5, we multiply our answer from step 4 by our answer in step 3. So take your answer from above and multiply it by 13, 26. Oh, that is not 26. Let me quickly undo that. So that would be 13 and then 26 and 72. So now I have a 3 by 3 matrix multiplied by a 3 by 1 matrix. So the result is another 3 by 1 matrix, and that'll give me out exactly the information I need. The first entry is 15.25. The second is negative 10.05. And the third is 1.75. And these are the values of A, B, and C. So we can go back to our equation and write this out as a quadratic. The constant term is 15.25. And then the linear term is minus 10.05x. And then the coefficient of the square term is 1.75. And just like with the linear example, we can check to see if our work is correct on Desmos or a TI graphing calculator. We can, if we're using Desmos, we can type in the same setup as we did before. That wasn't it. Thought I was being clever there by saving the code from before, but I forgot. I copied a link. So, so I'll do y1 tilde, and I'll do a sub 0 for my constant term, and then a sub 1, x sub 1, and then we'll do a sub 2 times x sub 2 squared, x sub 1 squared, sorry, it's the same x as before. And when we do that, you get out this beautiful parabola. It fits it really, really well, right? We don't see much of a gap between the green dots and the black curve, and the parameter values that Desmos calculates for us come out exactly the same as what we calculated when we did our matrices. For the statistics folks here, I also calculated residuals. That's the vertical difference between the actual point and the approximated point on the graph. So we have some positive residuals, some negative, but those amounts are really small. Great correlation here, r squared. So this worked out pretty nice. So that's how you extend the process out to a parabola. I hope you enjoyed this video as much as I did. Have a great day.